with that more complicated formula when rectangular and trapezoidal have this simple formula. So I'll just do this derivation for the rectangular rule, and I will not really go through the details with the other rules, but I'll give you what the truncation error is. Okay, so truncation error tells you what is the inaccuracies introduced by using a delta x versus delta x, which is non-zero, versus choosing something which is very close to zero. So here, let's say y of x is integral a to x f of x dx. Okay, where clearly x you can put equal to b, and then you'll have your integral. Okay, now what we can do is we can do a Taylor series, which we learned in probably the first chapter in this course about yi, which is y of x of I. Yi plus 1 is yi plus delta x y prime plus delta x square divided by 2 factorial yi double prime cube 3 factorial y triple prime I plus this O indicates what is the order of the next term. So it's delta x raised to 4. So that is basically we'll have delta x raised to 4 there, right? And assuming that delta x is small, then those terms really don't start really not mattering much. Okay, now what we can do here is we know this is from this expression, we know that y is f of x, which means that y prime, which is the derivative of this, is going to be f of x, right? And y double prime is f prime x, and so on, right? It's just the derivative of integral. So what we could do is we can write yi plus 1 is yi plus delta x. So yi prime, let's call this 1 and 2. Fi y prime Yeah, this is just to indicate that it came from 1, that came from 2, this came from 3. Okay, but what is this integral? Y of x equals, here let's just take xi plus 1, f of x dx. That's simply y sorry, I'm just not writing it this way. Okay, so the integral here is, well, it's y of x, but it's between two limits. So to compute the integral, just do it this way. There's xi plus 1. There's fi plus 1. fi. Now, y is integral of f of x. So if you want to find the integral from xi to xi plus 1, it's going to be yi plus 1 minus y of I. This is basically the exact value. You basically find the integral, you sub in the value of I plus 1, and you sub in the value of I. So this is my exact value. What the rectangular rule does is, if you recollect, it's delta x divided by, sorry, it's just delta x times f of I, right? This is the rectangular rule. You basically assume a rectangle whose height is fi and width is dx, and that is your integral. I'll come back to this equation just a bit. So the error, or the truncation error, is yi plus 1 minus yi, which is the exact integral, minus delta x times fi. So this is exact. This is rectangular rule. Okay, now let's use this equation here. Let me call it, since I've already won 3, let's call this 4, this equation. So from equation 4, we can see that the truncation error is, you basically take this, subtract yi and delta x fi, and you're left with delta x squared divided by 2 factorial fi prime cube 3 factorial order of delta x4. Okay, so when we're looking at truncation error, it's basically the highest order. So you can see that the truncation error is of the order of delta x square. It's proportional sign. So you can understand the size of this, right? So if you take delta x equals 0.1, the error is going to be approximately square of that, so 0.01. If you take delta x as 0.001 or 1e negative 3, the error will be 1e negative 6. So the smaller the size, the better, the smaller is the truncation, and the better is the estimate. But you don't want to go too small in the size. That's the other thing. So this is the truncation error for rectangular rule. Now you could do the same kind of calculation analysis for trapezoidal, Simpson's 1/3 and Simpson's 3/8. And what I'm going to do is I'm just going to give you what the truncation error looks like. Okay, what order it is. So I'm just going to write put a table and give you all the truncation errors, and then we'll use that truncation error to do something clever with them, which is the next part. So here is a table of all truncation errors. Let's make a table of rule versus truncation error, rectangular, trapezoidal, Simpson's, one-third, Simpson's 3/8. Okay, so the truncation error we just wrote down for is proportional to delta x square. Turns out that the truncation error for the trapezoidal is delta x cube. the truncation error for Simpson is delta x raised to 5, and then the 3/8 is the same, delta x raised to 5. It's a little smaller than, it's very, well, it's actually kind of comparable with 1/3. So this is okay. So if you want to understand the implications of this, let's say that you're looking for a tolerance of 1e negative 5. Okay. So you want your calculations to be accurate to this number. This is how much you want your calculations. So what this was saying is that if you want to now go with a method of your choice to get this kind of accuracy with the Simpsons, okay, so with the Simpsons, what you'll have to do is you need to take step size of 10 raised to negative 1, because the accuracy of Simpson is delta x raised to 5. So you will, error would be 10 raised to negative 5, right? Because be delta x raised to 5. So if you take delta x raised to 5, let me call this TE just to make my life easy. So the TE would be delta x raised to 5, which would be 10 raised to negative 5. Okay. If you want to use the trapezoidal rule, then what is delta x is that T is delta x raised to 5. So minus 3/5, right? No, 5/3. So when you do 10 raised to delta x raised to 5, sorry, 3/5. You do I'm doing something wrong. Delta x. So we want delta x. Sorry, this will be delta x cube, because that's delta x cube. So we need 5/3. So when you do this, you'll get 10 raised to negative 5. What is 10 raised to negative 1? It's 0.1. Let me compute what 10 raised to negative 5/3 is. 0.02. And then if you want to use rectangular, what should delta x be such that your T is, well, it's delta x square. That should come out to be 10 raised to negative 5. So in order to get 10 raised to negative 5, you would need to take minus 5 divided by 2. .003. So the same accuracy all of them giving you a total error of 10 raised to negative 5. That's your tolerance. But look at the step size. You need to choose 0.1, 0.1 is kind of big, right? Compared to 0.02. It's 5 times big. And then this is 0.02 is at least 10 times bigger, little less than 10 times bigger than 0.003. So you can actually get the same accuracy with a big delta X with the Simpson rule. So why won't you use the Simpson rule? You'll definitely use the Simpson rule because it'll reduce the number of calculations you need to do. And that's why you want to go for a higher order rule.